So good afternoon, everybody. I'm happy to welcome you here this afternoon. My name is Melba Crawford, and I'm the Associate Dean for Research in the College of Engineering and a frequent collaborator with people in ABE, so I've seen many of you and know many of you. We are going to have a presentation by Monika Ivantysynova today that's part of our celebration of faculty careers, which you all know Monika, but you may not know about this program. It came about as part of the College of Engineering strategic plan and the Faculty of 2020. And it's tries to provide the opportunity to recognize that our careers evolve. Okay, so it's a celebration of what we've accomplished, but also of where we're going. One of the things that those of you who are students may be surprised at is that we end up in far different positions in the long run, doing work that we were not originally trained for over our careers. There was also a desire for faculty to have something meaningful relative to the post-tenure review. So we go through the process of promotion and tenure, and then later in our careers, there is supposed to be a post-tenure review. And so every 7 years, on the average, then all full professors will give a presentation such as this to share with their colleagues and friends what they have accomplished and where they are going. And then after that, then they meet with their heads who are going to be greatly surprised, I'm sure, at the direction they want to go. No, not really. But to help plan a strategy for the future. So this is a new program. It was started last year on a pilot basis, and then in the 13-14 year, it became implemented as part of our standard procedure. So one of the things that we also do is we can't tell too much about the faculty member who's giving the presentation because it's their story. But I will tell you that Monika is the Maha Professor of Fluid Power Systems and, of course, the Director of the Maha Power Research Center. Many of you have been out there, very impressive place. She completed her PhD in the Department of Mechanical Engineering at Slovak Technical University at Bratislava some time ago. And she joined us here at Purdue. She paid me for that. No, she joined us here at Purdue a little more than a decade ago in 2004. And one of the previous associate deans for research had shared with me the experience he had in actually helping to recruit Monika and to get her and her equipment here. So it was quite a journey that, literally, that Monika's been on, and I look forward to hearing more about it from you.
Thank you, Melba. Yeah, thank you for your nice introduction. Ladies and gentlemen, good afternoon. I'm delighted to be here and to see you here, and I would like to share some of my experience and our research with you. I entitled this presentation From Gutenberg to Cloud Printing and From Bramah to question mark. So I will use my introduction to come back why I chose this title in the introduction of this talk. Then I will talk about one of our new technologies, displacement controlled actuation, and I will explain what that means and what we have done in this field. Then I will talk about hydraulic hybrid systems. We have researched and we are researching on this topic. And the third area of research I would like to share with you is dealing about pump and motor design, but where is the biggest secret, the secret of the fluid film, and I will talk about that. And finish my presentation, hopefully we'll make it in this time, with sharing some of my future plans with you. So if we look, Gutenberg invented the print technology in 1450. This is long ago. But I don't want to talk about Gutenberg, but I want to talk about something we all know, the typewriter. The electric typewriter, and look at this, it's just a 120-year history. And where we are today, cloud printing, this is my invention, but you know what I mean. So we use now other devices to make our papers. And what that means, the technology of the last century had to disappear. There are no electric typewriter manufacturers anymore. So where this brings us in my area of research, where Bramah invented the hydraulic press, and that was the starting point of hydraulics going in industrial use, 1795. And just you don't need the details, but this circuit I'm showing here shows the circuit of the last century, because typical valve-controlled systems everywhere used. But unfortunately, what is the technology of the 21st century? That's my question mark, because I'm working hard with my team to change the technology in fluid power from last centuries to something we could expect as engineer in this century. So, state of the art in fluid power. And I know that they are not all specialists here in this room, fluid power, so wait with me, I don't want to explain all the details, but I want to give you the big picture. So what I have circled in red are my typewriters. I want them to disappear. I do not want that industry is continuing to manufacture something which is really bad, creating a lot of energy losses, heating up our systems, wasting money, wasting energy. So these are my typewriters. And there are a few more, because we are wasting at least 33% energy in those valves still, which was good for the last century, but it's not good for our century. There are pumps and motors in each hydraulic system, which also are of low efficiency. But to invest in higher efficiency of pumps and motors is more or less not a thing you should do unless you don't change the architecture. Once you keep those valves, the investment in better pumps and motors is meaningless. You will not get the payback. And there is something more. Human control should be replaced by automatic control so we can do effective engine management. Hydraulic systems are basically energy transfer systems. So we need always a prime source of energy. And in most of the cases used in transportation sector, the primary source of energy is a combustion engine. So we want to do the entire system very effectively, and that's only possible with complete new architectures. So to conclude this here, throttling valves are my typewriters. And the second, pumps and motors are still designed in a very inefficient trial and error process. And in the computer age, we would like to come to computer-based design, and that would allow to improve efficiency of pumps and motors as well. So, major question being answered with my research or the research of the Maha lab. How much can performance and efficiency be improved by or through the introduction of new system architectures, more advanced and new components, and new control algorithms? So, and the question is this transformational? You will see, yes, that one of the reasons that's so new that a lot of industry does not want really to make this step, even if it would make a lot of sense. So, what's the Maha system approach? We want to achieve major energy savings through throttleless actuator technology. So, removing those valves and using direct pump and motor control for every actuator. Very early on, we started with a pump-controlled rotary actuator, pump control or displacement control, and I might use later on in this talk DC, so meaning we use the pumps and motors. So there's two effects of that. Not only that we avoid throttling and we have better energy, but we can also have energy recovery. Because in all situations where we have aiding loads, our pump will automatically run as a motor, and we can use this potential energy or kinetic energy back. So energy recovery without adding any components. Very nice thing, no throttling. That is what we want to do. But unfortunately, this changes completely the architecture of today's hydraulic systems, because suddenly now each actuator needs its own pump. And this is something like, oh my God, so many pumps. This question is very often asked by industry. But I think it makes all sense. So we want to use more pumps, but we do not want to use throttling valves. I want to explain an invention we made in 1989. We did not patent it, we published it directly. But this pump control concept is easy to use for rotary units, rotary motors, or double rod cylinders. But I'm showing here, you see that the cylinder on the right is so-called single rod cylinder. So there's a problem if I use a pump with the unequal flow conditions. If you see, the pump delivers flow to one side. From the other side, the cylinder is not giving as much flow to the pump. So we need somewhere to balance this unequal flow. And we came up with the idea to balance this on the low pressure side. So, and in aiding load conditions, that's the force moving the cylinder, we can automatically have the pump running in motory mode and giving torque back to the shaft. Something very easy, not anymore too many variables to be controlled. So in summary, this technology has a lot of advantages. Less components, the circuits look easier, so system simplification, less fuel consumption means lower operating costs, less heat is generated, we can reduce the cooler. Machine functions can be much easier realized by software, so easier to control. And something we learned from some of our prototype machines, improved operator feeling and higher productivity, simply because now the operator is operating each function independent of the others. So I have here some prototype machines we worked on. One more time, 1998, we published first time that solution. We built then a machine 2001, 2003 a second one, and measured fuel, and you see the fuel savings are 15 to 20%. In Bordeaux 2007, we had a skid steer loader with this technology, 15 to 20%. And then with the introduction of the ERC, we finally started working on an excavator, and here fuel savings of 40% were demonstrated 2010 with that mini excavator. Now I will talk a little more about that mini excavator, which is the test bed of the ERC. We are now a little what we're actually doing, what's the research about. Of course, we need to have models of the system, so not only model of the hydraulic system, but models of the mechanical system as well. So we run co-simulations to predict what will happen, to predict the performance of the system. And so we started also that project in the past. We predicted for a typical digging cycle that the energy of the current machine, energy consumption would be as follows. And that, I think, is an eye-opener. If you see the pie chart for the typical trench digging cycle of the excavator, this is current technology, what I said, last century, 43 or 44% are lost in the valves. Then we have 25% is lost in the cooler, which we have to implement because we are turning so much primary energy into heat. And then we have friction losses, of course, we have pump losses, and at the end, from the energy provided on the engine shaft, 14% is used only for work. That's crazy, is that? 14%. So that was simulation, but we instrumented a machine and put sensors on and did verify our simulation model. And then we used the simulation model for the new system we proposed. I will fly through, but you see now each of the excavator systems, the bucket, stick, the boom, have their own pump. The swing drive has its own pump, and we share these with some other functions which are not always used. Now that's the new system architecture, and let me share with you how this system now is using energy. 39% less energy is consumed for the same cycle. This is the pie chart. I do not have them on one next to each other, but this pi is much smaller, 39% smaller. And now how is the energy here distributed? So the charge pump losses are now 23% because the entire energy is not so much. We have cylinder losses. We have now 39% pump losses because many more pumps are there. And coming to that, it makes then sense to look at pumps and to improve their efficiency. And now 25% is actuator work. We improved. But now, if we would improve pump efficiency, we could even more work do for the actuator. So this machine was borrowed by Caterpillar in 2010, and they did a side-by-side test with a standard machine and this Bobcat Purdue modified technology. And the measurements results are here. They tried to do the same work, same soil loaded, and the fuel consumed is nearly 40% less for our prototype machine. And the cycle time was faster, which brings us to another table where you see how Caterpillar is introducing an efficiency term in terms of ton soil removed per liter fuel burned. So, and you see the efficiency improvement of that machine is nearly 70%, 69%. Now we went ahead because this seems to be a problem that so many pumps need to be introduced. So we worked on pump sharing for all those actuators which do not work simultaneously. Can we bring in switching valves and can we then switch different pumps to different actuators? Also during machine operation, of course, without giving a hard feeling to the operator. And we patent this principle. Patent was issued in June 2012. We have it in between implemented on our excavator. Last year I was very lucky that we could first time present displacement controlled steer-by-wire system. So also pump control used for steering. And this system was implemented on a wheel loader, which is really for the wheel loader for this equipment, the world's first hydraulic steer-by-wire system in this way. Not only that we reduce, of course, fuel consumption, but the system applied on steering has some other advantages. Energy efficiency, yes, but also variable steering ratio. So it's more convenient to steer. It's easy to implement, dependent on vehicle speed, and also variable steering effort. And we demonstrated also autonomous operation. And if it works, I have here a video. And you see the wheel loader in the Maha lab operated autonomously. So that's something a steer-by-wire system, of course, offers. So now I want to switch to next topic, hybrid systems. Hybrid systems on powertrains. You all have heard a lot about electric hybrids because that is full of everywhere, electric hybrids. So what's the motivation? At the moment, fuel prices drop, but we will see that they will increase again. And by the way, it's not just the price. I think we all engineers should work on that we do not waste energy. So we should be careful and use our energy right way. 69% of the US petroleum consumption is going to the transportation sector. And in the transportation sector, there are many, many areas where we currently still waste a lot of energy due to very inefficient systems. So fuel savings through hybrids, so just in general. So of course we want to have a kind of regenerative braking, reuse the brake energy. We want to have engine management effective and an efficient transmission concept, and of course efficient and high and light components. Now all these factors, we have an answer in hydraulic systems. So the hydraulic hybrid is the counterpart to the electric hybrid. and can do some of the things just better, but most importantly, much cheaper than the electric hybrid. So what I have here, and I might explain how actually it works. So all what we need, a combustion engine, a pump and a motor, and accumulators, a high pressure and a low pressure accumulator. And then we can drive, so it's a continuously variable transmission, which then transfers the power from the engine to the wheels. Now, in case we want to brake, our motor will now run as a pump, take energy from the low pressure accumulator and pump it in the high pressure accumulator. And here, that process is very different from the electric hybrid. Where doing a braking maneuver, you basically cannot charge the battery so quickly. But we can. We can charge our accumulator very quickly and store the brake energy in this accumulator. And then what we can do, reuse it during propulsion. So if we accelerate our vehicle, we will use the accumulator power, stored power, and propel the vehicle without using engine power. So what are our research tools and what are past projects? Let me just talk a little about. So likewise, we use a lot of models in our system about displacement control, but I just talked the last few minutes about. Also in those powertrain and hydraulic hybrid area, we are strongly using MATLAB Simulink and models. We have built libraries for very different powertrains where we have also models for engines and of course empirical models for our pumps and motors so that we consider real loss behavior of those components of a powertrain. Now, with this, that's not the only tool. We have also used, and I'm not 100% sure to say if we are one of the first, but maybe not the first, but one of the first groups who have used dynamic programming, a technology which is used for comparing performance of controllers for sizing. Because we found that sizing in a hydraulic hybrid transmission is much more complicated, and when you size it just statically, you might not come up with the best solution. So we went ahead, and I'm thankful to my researchers who came up with this idea to use dynamic programming for sizing, dynamic sizing of hydraulic hybrid transmissions. And in order to do this, we had to use our parallel computing cluster. I have here an example. Just to run 2,000 designs would take 5 years, but running with our own computer cluster, we could do the same thing in 5 days. So I think this is impressive, and I would like to thank my students for creating this all. This is all the work of my students here, what I'm presenting. So that's our cluster, and here you see another research tool. We have two very strong hardware in the loop test rigs for testing transmissions. What I'm showing here is one where you use electric machines to simulate the engine, and another electric machine to simulate the vehicle dynamics, the vehicle itself, and what is in the hardware is in the middle, our whatever transmission we might want to test and whatever control concepts for this hybrid transmission we want to test. So this is very powerful and has led to a lot of nice research results in the past. We have also done research on power split transmissions. Power split transmissions have made it first on the in a large amount on the market in agricultural tractors, and I was involved more than maybe 15 years back with this technology when it came and made first to the first tractors. That gave me the opportunity to think about, is this architecture what you see here involving a planetary gear set plus a continuously variable transmission in parallel, can we use such an approach also for a hybrid? And the answer is yes. We patented this solution here at Purdue. You see there's even 2 patents issued. A power split hybrid. This is, to me, the transmission of the future. So this is the transmission we should use in all kinds of vehicles if we care about efficiency. Due to the parallel arrangement of a shaft, mechanical shaft from the engine to the wheels, and the continuous variable transmission, we can do very, very efficient transmission concepts and effective engine management. So what I want to share in the next few minutes with you is some work we had to do on the side while taking this power split hybrid from an idea on paper to a prototype tested in the lab. But because this was work very confidential and with industry done, in parallel in order to publish, we worked on the hydraulic version of the Toyota Prius. Here I'm showing the powertrain of the electric Toyota Prius, like it is in the car implemented. And I'm flying in the parameters, but we don't have time to go into these details. But if you see, we have a planetary gear train. I don't know, see my mouse? No, sorry, and I didn't bring a laser pointer, very bad. So that planetary gear train, the electric motor, the electric generator, both are here. And we replaced this with the hydraulic version. So you see, again, we have a planetary gear train, but then we have a pump and a motor and high pressure and low pressure accumulators. So this was done in simulation first. We sized the system. Here you see unit sizes and 20-liter accumulators to store the brake energy of a Prius. And then I want to share some results. We simulated drive cycles. The UDDS is a very standard drive cycle, and we achieved with our hydraulic version 62 miles per gallon. And a highway cycle, we achieved 60 miles per gallon in simulation first. Now I will share with you a comparison between our development and what you can find on the Toyota website for the Toyota Prius. So our hydraulics solution, not only that it's much cheaper, is 33% better on the highway and 30% better in the city. So that, I think, are amazing results. If you think that this was done by my students just on the side, while we were working on a much larger hybrid transmission together with industry. So here you see some results out of the simulation, just comparison here, not the electric Prius, but a vehicle with manual transmission. And what you see, this is the engine map, and the white dots is engine operating. So with a manual transmission, you operate everywhere, also in areas where the engine is not very efficient. But once you introduce such a concept, same is possible, of course, with the electric, the hydraulic hybrid, you can now operate the engine in much better, efficient regions and not all over. So that saves fuel. So I show here the Prius. We realized this concept also on a test track, but I would say that is, of course, not integrated. You see the original Prius planetary gear train and then pump and motor added to our powertrain test track. And the results we here achieved on the test track. Next slide I want to show, and this is the only slide I have about, more or less 4 years research together with Parker on the same concept what you have seen just. That is the transmission we developed with them for FedEx Class 6 vehicles. And now they went in production. This is first time in Parker's 100-year history that they did not acquire a company and bought a product to go in production, but they built this on our development and have now a division selling this concept. Okay, current research in this area, and I'm very proud to share with you that we had another very good idea. If I say we, I should rather say one of my students, and he is here. Mike came up with the idea of a so-called blended hybrid. And we decided not to patent it, but published this 2012 on a conference in Russia. Now, what is this about? We with few, I think with few little elements, which are not very costly, we can make a hydraulic hybrid even better operating. So we have 2 motors, 1 pump, And that allows us what we call a so-called hydrostatic driving. So the accumulator is not part of the system. That allows to go below the accumulator pressure, and the lower the pressure in the system, the higher the efficiency could be. But if we brake, and I think I have that now, braking, then our motors will work as a pump, and we store the energy like in any hydraulic hybrid in the accumulator, and the accumulator pressure is going up, and we have it stored. And then follow up, if we now came to stand still or whatever lower velocity and we want to propel the vehicle again, we can use the accumulator power now to propel our vehicle. So this has, as I said, certain advantages, and we are going further to implement this in a car. I will show you at the end what our plans are. Now, I talked about power split. Also, this blended hybrid can be part of a power split, so involving again a mechanical gear train here, a planetary gear train, together with the hydraulic blended hybrid, which improves efficiency further. Of course, it's more complex and therefore also more expensive. Now, there is something we work on which combines the two technologies I just tried to explain: displacement controlled actuation and hybrid transmissions. There are a lot of working machines which have working cycles. They involve driving, and mostly these are heavy machines, so there's a lot of kinetic energy which could be gained back if we implement in those vehicles also hybrids. And I will share with you some work we did on a ridge staker. This is this machine here staking containers in a harbor in a few minutes. But before going there, I talked about our test bed, the excavator, the mini excavator, which roughly has this circuit. See, for each actuator, main actuator, one pump. And then that was the result. Caterpillar measured the 40% fuel savings, if you remember. But we went further and replaced the swing drive with a hybrid version. What does allow now is we can store the brake energy of the cabin swing. And why we want to do this? That allows us to downsize the engine, because now we have a little power stored and we can make up some peaks. We filed a patent for this, and it was released. And here you see typical working cycle. What I'm showing is the required power of that cycle. Now, for the mini excavator, the rated engine power was 37 kilowatt. But that doesn't matter, a larger excavator would be more. But if we bring a hybrid in, so a meaning of storing energy, brake energy, then suddenly we have this stored energy available, and that allows us to downsize the engine to half. What brings that? Remember, I said 40% fuel savings. We can now achieve 51% of fuel savings. At least this has shown our simulation. We did not downsize the engine of the excavator because this is a lot of work, so I don't have really measurements, but I trust our simulation that it would be around about this. Now, a few minutes about the reach staker. The reach staker is a machine which really involves a heavy loads, first of all, but also a lot of short driving and braking. And being a heavy machine, a lot of energy can be recovered. So I give you an example just to have an idea how big the engine is: 280 kilowatt, the entire machine 77 tons, the container mass 45 tons, so top speed 25 kilometer per hour. So it's just to get an idea, and that's a typical drive cycle. Now, if we go and look at what is actually available on energy when we stack these containers, so potential energy, 5.1 megajoule. That's a lot, which can be, if we have a hybrid, recovered. Or displacement control. So this, I should say rather displacement control in this case. And the brake or kinetic energy, unloaded and loaded, 1.9 megajoule. 1.7. That's another large amount of energy. Now, the hydraulic system currently in those machines implemented is last century. We have valve-controlled systems, we have power shift transmissions. None of these subsystems allows any of these to recover energy. So we replaced the boom circuit here, the valve-controlled, with our displacement-controlled version, which now allows, when we lower the boom, to recover this available potential energy. And I'm still working here with this animation of Mike, which is not working so good in my computer. We further replaced the power shift transmission with a power split. The names are similar, but very different in efficiency and operation. So we have, again, a planetary gear train with our hydrostatic transmission. And on the top, we added, so this is the DC actuation, which I talked at the beginning of my talk, then power split, very efficient transmission concept. And here we added a hybrid, another storage device with a pump. And this architecture worked, or seemed to work best in order to get the highest machine efficiency. I will show you some simulation results for a typical stacking and unstacking cycle of this machine. In average, the results are 47.9 is top average reduction while unstacking, while stacking 30%. So in average, 38%. Now you need to see, this is a huge machine consuming a huge amount of energy. So that, I think, is a very amazing result. So now with that, I have 20 more minutes, and I want to come to my third area of research, new design methodologies for pumps and motors. Remember that in current systems, they have all been designed in a very, very expensive trial and error basis, and that brought us to a technology status, and you cannot go beyond. But with computer-based design, I think we can make a big difference. So I will talk about the secret of the fluid film here. So what do we want to do? We want to design pumps which have better efficiency, smart pumps with advanced pump controls, which are suitable for the displacement control circuits I proposed, increase of power density, and lower noise emission. I cannot talk about all of this, but will concentrate on the computational effort here. So, what's the future in pump design? Do we need new principles? My answer is we want to go rather an evolutionary versus a revolutionary development. We want to improve current designs by understanding what's actually are the physical effects which work in those pumps which have been designed like a black box. It works, but why does it? So we want to get this complete understanding of physics. We have built, and there's a need to build multi-domain models, write code, to understand, to verify those models with a lot of different experiments, and I will share some of them with you. And of course, to improve the models, to cover the main effects better, and to develop finally code which can be used by industry. So what's actually the most critical element? The lubricating film, that is the secret. I said there are lubricating gaps, and I will show you this on two different designs. On the left, the exopiston machine, on the right, the radiopiston machines. Both machines are heavily used in current hydraulic systems, and they have in common the piston-cylinder interface, a slipper interface, and the cylinder block valve plate or control journal interface. Now, what's so complicated on that? These interfaces have two functions to fulfill simultaneously, sealing and bearing. In mechanical engineering, we have seals and we have bearings. But these elements, unfortunately, have to do both functions as good as possible. However, usually it's controversial. You have a good seal, that's a bad bearing, and vice versa. Now, how we tackle this? We need to understand what the fluid film does there. It determines friction, leakage, load carrying ability, But the biggest unknown is how is this film actually created and how gets it stability. So how does the fluid film is created? We know that there's machine kinematics. I'm showing here kinematics of a moving axial piston machine. We know that there are design parameters, clearances the designer has in his mind or her mind, and that plays a role. That is known, this is no surprise. But what else plays a role? And that's the question here. Now, we discovered many years ago, or let me start first here. We know that we need to have a certain load carrying ability of the fluid film. If we analyze here this axial piston machine, we know what forces acting, pressure forces, friction forces, spring forces, centrifugal force, reaction force of the swash plate. So these are all external forces acting on an interface, but then there's a fluid film separating highly loaded parts from each other. Now, we can get stable film only when the forces, these external forces, are balanced to avoid wear. So if you look a little deeper, this is the piston cylinder interface where we have again the highly external forces, pressure force, all what I mentioned already. And the trick is we need to come to a point where we have a stable film, force balance between axial and fluid forces also for this interface. So if you look a little closer, we know the kinematics, the piston is moving in and out, the piston has a rotation, spin motion, but then there's something you see on that right figure, something we discovered maybe 10 years ago, that there's a micromotion of very hard dynamic loads reacting to it, which we need somehow to model and to understand because it plays an important role. So far, so good. What next? So here I'm showing one more time, this micromotion is acting also on other parts and is present and has to be understood. If you look a little to fluid mechanics, I'm showing here an equation which comes from Navier-Stokes Reynolds equation, which actually is used to calculate the pressure in that thin film. Now, and that equation can be more complicated. I have a very easy version here. H is the film thickness. So the derivative of the film thickness with respect to time, say, is there. So has an impact on pressure buildup. It has to be understood. So if we want to have the real load carrying ability, we have to understand how this micromotion is. It's in literature also known as the squeeze film effect, which contributes to load carrying ability. So we have to model that. Is this all? Unfortunately not. So what we discovered also several years ago, that there must be something else, because we used all what I said and tried to model that cylinder block valve plate interface, but we run simulation, and our film thickness, shown here on 3 parts over time, was dropping to 0. But we simulated an existing machine. How can it be? If the machine survives, the film thickness cannot drop to 0. So our model must miss something. What was it? Something what we called here. This was without elastrohydrodynamic effects. What's that? Oh, when we started to consider how pressure load acts on the surface of the cylinder block, and we run a finite element model for the block, and considered these little pressure deformations, which are on the order of the film thickness itself, some microns. Suddenly, for the same machine, we got the film stabilized. So that must be an effect being present. Now, is this all? Unfortunately not. So fluid film at that point already was very clear, needs a multi-domain model, needs to describe complex thermoelastic fluid structure interaction phenomena. So I will show you a little the structure of our model here. So we have in the kernel of our own software fluid mechanics model describing the gap flow. Then we need to describe the micromotion I explained. From there, we get the squeeze film effect expressed, and we can calculate this pressure distribution of the film, that fluid film of some microns, dynamic pressure. What you see the change here is during the time a pump would run 1 shaft revolution, and then of course the process is repeating. So these dynamic pressure changes are there present. And you see those spikes? they will deform the solid structure. So we need a FEM analysis to consider fluid film thickness changes locally impacting the gap flow model. Now our fluid is viscose and viscosity changes with temperature and pressure. We did know that, but we did want to have a more precise description of our flow model. For that, we very early on already tried to have included a heat transfer model. So how it is heat distributed in the entire machine to consider locally the correct fluid viscosity. Now, after we arrived there, we found that also, and that was relatively recently, maybe 2 years ago, that there is thermal loading on the bodies present, which the thermal load is not evenly distributed and leads to additional deformation of parts, which plays a role, and we had to consider this. And I will show you some of the discoveries we made in this area. So that's one more time just the structure of our model. So fluid volume model for solving our fluid mechanics equation, FEM analysis inside our code with our own FEM solver for pressure deformation of the solid parts, and then heat transfer model calculating the distribution of heat in the solid parts of a pump, and then taking from there the thermal loading and considering also what is the deformation of parts to thermal or temperature distribution being not evenly in a unit. So once we solved this all, that we discovered some very interesting things, but one more thing here. One topic which was around at least for 3 years without any solution was that our parts, you remember that one picture where everything was moving? They are moving freely around. They seem to be held and stabilized by force balances. So if you ever run a finite element analysis, you know that you need to constrain your parts. But the question was, how do we constrain that freely moving piston in the cylinder? And we tried to constrain the part at very different, at the axis, at the head of the piston. But everything went to or showed us different deformation then. What's right? What's wrong? So finally, one of my former PhD students came up with a method. He found this applied in aerospace and some other areas, so-called inertia relief. So we introduced this, and now we are using it broadly for all the interfaces for constraining our freely movable parts of a pump. So the next discovery was, how do we deal with this thermal loading? That introduced a lot of problems because heat transfer is necessary to understand and to model. So boundary conditions need to be found for all those parts in order to be even able to simulate what would be the energy dissipated in the fluid film, how it is transported outside. And I will show you some. Here you see a cross sections through a cylinder block, and in the end case of a pump, you see that there are hot spots and there are areas where the solid part is of temperatures much less. So these differences in temperature lead to different deformation of the solid bodies. And here just one example, considering the deformation of the block and of that valve plate end case, gives us, without deformation, a fluid film of this thickness. And if we consider the fluid film thickness, which, remember I said, is top secret, we don't know, is different. So the answer is we had to, step by step, add all these phenomena to our model to finally come up with something which is of practical meaning for let's say, industry to design pumps and motors. So we did a lot of work in validating our step-by-step in more complex models. One of the test tricks we built is shown here. We designed a pump which would solve only the problem for us to measure directly friction force between piston and cylinder. I will show you the cross section of this pump here on the top left. So we have telemetry to wireless transfer, the friction force sensor signals. What that gives us, the friction force, if the film thickness is right, is a parameter our model should exactly be able to calculate. So we wanted to compare this with measured data. And I show you, next slide, some of the results. You see the measured data in blue. The green data was what several years ago our rigid model gave us. So friction force is off. It is friction force of a piston cylinder over 1 shaft revolution, what you see of the pump here. And finally, our fully coupled came close to the measurements. So that's nice to see, but there are still things to investigate, and unfortunately I don't have the time to talk about all these details. But I want to share, we built another, I think, exciting test rig to confirm that these local surface deformation due to pressure, which are highly dynamic, and we had doubt about if the metal can deform so quickly, if this is true. So we built a single piston pump where we were able, around that piston, to implement a lot of pressure sensors to measure whether the surface deforms. How would we measure? By measuring directly the pressure field. We did know from simulation that this pressure field I'm showing on the bottom looks completely different whether we see that the surface is rigid or the surface deforms. So here you see that cylinder block with pressure sensors implemented, thermocouples around very close to the film, the thermocouples directly at the film, and 2 millimeter the pressure sensor away from the film. Now we had 9 pressure sensors. This was the smallest at the time we could get. So we had a nice idea here to make the block moving around but in a fixed and controlled position. So at the end, with turning the block 180 times around, we could get to a resolution of the measured film, pressure film with 1,620 points. At that time, it was more than our simulation grid. So here you see the completed pump, and next slide I will show you some results of the measured pressure in that fluid film between piston and cylinder. You see that's the piston length here and the circumference of the piston. So we see that film basically unwrapped, and high pressure in the displacement chamber over 1/2, and now suction pressure goes down, and those peaks are hydrodynamic effects which are caused by deformation of the surface. So with that, I think we confirmed this deformation is present. Now going ahead, we measured also temperature profile, and here compared this measured profile, which is stationary, at steady state, it doesn't change once the pump runs at certain conditions, and the simulated one, you see we are very close. So we believe we have nearly discovered everything happened. We did some other measurements. Here you see again simulation versus measurement on a valve plate, and the temperature distribution again. Several years back we did some similar experiment, and we were not capable of measuring these hot spots here. Simulating. We measured these hot spots on both sides, but our simulation model was not able to see them. And I remember, will never forget, one of my PhD students who already finished his work when he entered the lab told me, Monika, this is because our model is laminar, and perhaps there's turbulent flow, and if you would model turbulent flow, we might get these hot spots. I told him, that's not true, Marco. There can never be turbulent flow. That must be something else. But I had no answer what it is. But he discovered this because he was the guy coming up with the thermal loading, so implementing in our model that we now would also consider how much the surfaces deform due to thermal loading. So the thermal loading made the film thickness in these areas smaller film, more friction, more heat generated, and that makes up the temperature. So now we know. But he did not know, I did not know, but we made it together to this point. So I see time is running. I will, if you allow me to go out of this and go a little later in, because I've had too much prepared here. I did know that that would be a problem. I just don't know. Bear with me. I want to share one thing here. One thing, I think, and I go fast, I promise. So some opportunities we see out of this research. Many years back, one of my former PhD students studied a different shape of the piston, but we had a rigid model. It tried to work fine. But now we did some research modifying surfaces in another way. On one of these surfaces, which are normally flat, and industry is controlling flatness to very, very low tolerances. Oh, this flipped out. We introduced a sine wave. Let me show that. And what the sine wave does. So we see film thickness there with a sine wave of that plate plus minus 1 micron. So it generates hydrodynamic pressure buildup and increases load carrying ability of the film. And with that, we were able to reduce friction or power loss by 60% in that interface. Imagine plus minus 1 micron. People said, this you cannot do. Here you see what it does. So this is the plate. Okay, this exercise, you don't see plus minus 1 micron this way, but you see the film, how the film differently looks in simulation from the flat to the waviness of the plate. And we patent this. We did also do a prototype, and that's the prototype. The plate was made in Germany. We measured, and I'm very proud to report that we measured 10% overall efficiency of movement by this little change to a surface. And manufacturing is going ahead. There are now a lot of technologies available to realize such designs. So now we are working on waved pistons, and we are even getting crazier. We want to introduce also waviness of the cylinder. We had just a company visiting us that they told us it would not be a problem to make such a cylinder. And you see results, 50 up to 80% reduction in energy dissipation by these changes. Now let me one more time go out, because I want to be in time. So, and this would be the next, to share with you my future plans. So what do we want, where do we want to go? Digital prototyping, I think that's the future. We want to demonstrate industry that they can design pumps and motors with much less money to be invested, and with much more ideas to be used, because we would design on the computer and have the analysis done on the computer before going and making hardware. And that will reduce costs, and that will allow to use these new ideas, surface shaping, new material combinations, new manufacturing technologies. We are planning to demonstrate this with our own Maha pump. We are currently designing, and we want to manufacture and want to demonstrate that this can work. Another thing I want to announce, we are currently working on the Maha hydraulic hybrid. This is the car we are currently modifying to hopefully run in the summer with a hydraulic hybrid, and exactly the new one, the splendid one, what Mike is the author. And yeah, we are proud that industry is interested. Most of the components which will go in that vehicle, we are getting donated, and I hope we can demonstrate that a hydraulic hybrid car is capable to be designed and will drive nicely. So there are also some big dreams and challenges. I tried 2 years ago to set up an STC, Science and Technology Center for Water Hydraulics, and I haven't completely given up this idea. We are working on water hydraulics, and I believe this is one of the technologies which should enter the 21st century, because we have only roughly 110 years of history of oil hydraulics. The Bramah press worked with water. So if we all our computer knowledge with new other technologies around use, we might make this challenge and my dream reality and use water as fluid in fluid power systems under high pressure. That's the challenge. And another idea, I would like to see displacement controlled actuation as the choice for efficient and powerful egg robots for this century. So with that, it's just to show you my team. Here's the Maha team last summer. And I would like to thank all the researchers who allowed me to present this here. And with that, I finish. Thank you.
So we have some time for some questions.
Please.
How robust are the energy savings for your hydraulic hybrids to accumulator size? Is that an optimization opportunity?
Yeah, there is. It's not just the size, it's also your minimum pressure you have during the time in that accumulator. So it's a lot of values. Remember, that's why I'm happy that some of my researchers came up with the idea to use dynamic programming. So to use a drive cycle for sizing. So to investigate different sizes, what is the impact of the energy consumption at the end. This is something, these tools were not around. And it's, unfortunately, if you're in a company, you size it, you have invested a lot of money, you will not change it anymore. You are happy that it runs. So I think in an early stage to go through what is for a given vehicle and the given most often used drive cycle, the best size of those components seems to be very, very important. Yeah. Yes, please.
So on the water hydraulics, I guess in general I know some of the differences obviously, but what are the major challenges with changing the water as a fluid? Some are obvious. And then do you see the solutions as a material based, as an architecture based? What do you see some of the opportunities for?
The opportunity is what I said to here, the shaping. I see that this can be the breakthrough. If we manage shaping of the parts, so we're getting the last thing out of the fluid, we need to bridge this 30% basically lower viscosity. But if you compare this to current designs, and we are tricky, we get those shapes. So Monika, she's sitting there, she's working on it, and we have some very nice results already. Of course, it requires different materials, but I think the materials were never really the issue. The issue is today, if you continue with what all did with current designs, you would just change the material to make it with water. You leak so much, it's not working at high pressure. But if you use this shaping and maybe some other ideas you might come up during research, I believe it is possible. And then it would be just amazing, I think. Yeah?
Thank you for the great presentation. So I got a question in your research area on the electro-hydrodynamic lubrication.
Yeah.
So you research the lubrication between the piston and the barrel.
Yeah.
So it's very rich, very hard, the surface, right?
Yeah.
So do you think this kind of lubrication also can happen between the very hard shaft journal and a soft bushing?
Okay, you know, in those piston machines, we do not have always heart to heart like you described. Okay. Especially and I left exactly a few of these slides, but I wanted to show you something out. We do have today, especially those machines which work at very high pressure, brass, so a softer material going with steel together. So similar like in bearings. So but the deformations will be anywhere there. They of course will be different on what material you use.
Okay. So do you think that whenever we do a bearing analysis and hydrodynamic film thickness calculation, do we always always consider this elasto hydrodynamic?
I think if you want to have the real answers, if you want to have the real performance, you need to. We have done in the past, we had for many years just rigid models, and a rough, let's say a rough prediction of performance you will get with these models too. But where I believe it's critical, if I want to make that next step, I would like to design new pumps and motors based on this computer simulation. I need to make sure I have the main effects covered to avoid that, we do this all and then we build a first prototype and we crash it totally. So I want to trust what I'm predicting is real. So I need to go to these boundaries. For rough, it's fine. But if you want to have more, you want to know at these parameters it will still work, you have to have these effects implemented.
Thank you.
Any other question? Yes, please, Melba.
So one of the things that seems to be evolving is the need for more interdisciplinary work. So are you working with material scientists now and thinking about these new materials? You've discovered dynamic programming and people over in industrial engineering operations research, that's their bread and butter. Lots of opportunities. So where do you see sort of this intersection?
Okay, Melba, really to make the next step on this water, we have now a single project, but that was exactly if you come to critical areas where, let's say, all this needs to go together, there is interdisciplinary work more necessary than I ever have done. So what we did in the past, I think we could kind of live on an island, but if you want to go further, you need simply. It's not just material, there's also manufacturing technologies. What is available, what you can really do. And that has changed since I studied, and you got at that time the most important, what is now available. I was really surprised this company, which was visiting maybe a month ago, Maha, I never wanted to touch the cylinder because I learned the bore is very heavy to be manipulated. These tools to make a bore accurately is not easy. But they said, they can do it very easily. That's new. This is new manufacturing technology they introduced. So then that opens something. So suddenly I went to one of my researchers. So we should now run simulations. I learned that is possible to manufacture. I always was driven. I didn't want to do research in something which I believed can anyway never be made. It would be just for writing papers, I say sometimes. So I always was driven, I want to do something that industry can get and we can do it. But I'm open, of course, to change my mind if, there's something around and which brings us all forward. Yeah.
Any other questions? Well, we have the rest of the afternoon to engage and to eat what's left in the back and to catch up with the other 30 slides that Monika has. Thank you.
Okay, thank you.